Okay, today we will work on section 16.8 on Stokes' theorem, and let's start with the theorem. Let S be an oriented piecewise smooth surface bounded by a simple closed piecewise smooth boundary. Because this boundary is the boundary of surface S, then we can say that boundary is dou S. Just notation. Okay, we used this notation before. The boundary of a surface, a boundary of the solid, we can use that dou S or dou E to represent the boundary. Now, with positive orientation, and let vector field F be a vector field whose components have continuous partial derivatives. Partial derivative on in R3 containing S. Let's visualize this first. So suppose I have a surface. Suppose I have a surface S, okay, which is oriented, which means when we say a surface is oriented, at least for now we know that it means that surface has two opposite sides. Okay, now piecewise smooth means it doesn't have corner, and if it does, then it's a very localized corner. Okay, and then bounded by a simple closed piecewise smooth boundary dou S. So this is our dou S here. Let me use different color. This is our dou S. Which we usually call C, right? Now we orient that in a way that the C is positively oriented, and as you can tell, because it's positively oriented that way, then the S will be oriented outward like that, outward or upward. Now, and then the vector field that we have on in R3 actually has has continuous partial derivatives on the region containing that surface, including the boundary. Basically, when you do the partial derivatives, you don't get undefined. Okay, you don't get undefined. Now, so what this theorem says is the following. Let's say that we have that this situation, then line integral over closed curve C, which is the boundary of our surface S, of f dot dr, that is equal to double integral of surface S of curl of f dot ds, oriented surface S. Okay, so if we want to compute, for example, the curl of vector field f dot ds, one way to do it is to compute the amount of work for the vector field, or the in this case force vector, when we go around the boundary. Okay, now I remember one of my professor's lecture. I think this is how I memorized Stokes' theorem. even though that professor was actually explaining something else. He said this way. Okay, I tried to help you visualize the theorem. So suppose we have a force field or a vector field, basically. Okay, on that surface S. Okay, now of course those force field may create curls, right? Okay, we have curl. I know this may be too complicated for you to see for now. Let me erase the force field and end up with only the curl. End up with only the curl. So you see on this surface, in the interior of the surface, also right at the boundary, of course actually everywhere, right? You have the curl of that, the force field or the vector field. Now then what happened is the force field for the curl from this one, for example, this one here, okay, being cancelled by the curl from here. Now notice that this part, the one on the lower, like on the lower, it has this, that's the curl, right? But right above that, that curl is being cancelled. Okay, like this curl here, this is being cancelled by the curl from next to it. So you will see in the interior, all the curl get cancelled. In the interior, all the curl at this point here, the curl being cancelled, the curl being cancelled. The one not cancelled are the one at the boundaries. The one not cancelled are the one on the boundaries. I hope you can see that. Okay, like everything in between get cancelled, right? But the one on the boundary is not cancelled. So if you want to add, if you add all the curl, if you add all the curl of that vector field F in that surface S, then they all cancel except at the boundary. Okay. Now, so when you add the curl of that surface S, oriented surface S, okay, the interior, in the interior, all the curl cancel each other, and we are left only the sum of that vector field at the boundaries. Okay, now yes, that's what he tried to make sense of this. Okay, now of course later on I found out that what he said is not totally true, but he gave a very, very good visualization of what actually happened and why we come up with this theorem. Okay, now so that's the case. We will do some problems very soon, but instead of going to problems right away, let me give you some more things to think about. First one, notes. The notes. Note that if that surface S is in xy plane, which means it is flat, okay, and it doesn't have to be xy plane, it can be xz plane, can be yz plane, then the d-oriented S is basically equal to 0, 0, 1 dA. I wonder if you remember this, our ds. What our ds stands for? Our ds stands for the normal factor of ds, right? Okay, and if that n is unit, then we can say this is n dA. Maybe if let me clear that up. Suppose our surface is given by z equals to the function of xy. Then the factor normal to it, the normal factor, let me use capital N instead. The normal factor, but not unit, will be negative c sub x, negative c sub y, 1. Right? Okay, so this is normal factor ds. Okay, but then if we make it unit, that will be negative c sub x, negative c sub y, comma 1 over the magnitude, which is square root of c sub x squared plus c sub y squared plus 1. Okay, now in this case, if S is a flat plane parallel to xy plane, then the unit normal factor will be just 0, 0, 1. Right? Okay, and the curl of f, as you see, we have learned that before, is something dot q sub x minus p sub y. If the factor field is for factor field f equals to pqr. Okay, now with that setup, then if you see that therefore curl of vector field f dot ds is equal to dot q sub x minus p sub y dot 0, 0, 1 dA, which is equals to q sub x minus p sub y dA. Okay, now so integral over closed curve C of f dot dr equals to double integral over surface S of q sub x minus p sub y dA. Okay, that is if S is in xy plane, or to be more slightly more general, S is parallel to xy plane. Okay, so let's say this is our xy plane here. Okay, and then you have that surface S happens to be on the parallel plane. Okay, happens to be on that parallel plane, a plane parallel to xy plane. So we can actually do this, which, if you remember, this is basically Green's theorem. In other words, I have established that Green's theorem is actually a special form of Stokes' theorem. And Stokes' theorem is the generalized form of Green's theorem. Okay, Green's theorem being used if you have two dimension, okay, where the vector field being applied on only a plane, and Stokes' theorem in 3 dimension. Okay, now let's do some examples. I will pick 2 examples from our textbook. And of course, even though I say that I go over textbook, but I want to give more details or intuition into the question. So let's say we have this example here, and let's say we have this as our picture. Our textbook gives us the picture. Evaluate line integral over C of vector field f dot dr, where the f is this and C is the curve intersection of the plane and the cylinder. Okay, so we want to compute integral over closed curve C of f dot dr. Okay, which according to Stokes theorem, that is equals to double integral over surface S of curl of f dot ds. Okay, now there are 2 parts that we need to do on the integrals, about the integrals on the right hand side. First one, we need to work on the curl of vector field f. Now you may think the following: well, Thomas, we have line integral, which is 1-dimensional integral. Why do you want to make it double integral? There's a trade-off here. You see, this is like a single integral, which is 2-dimension, okay, and you make it double integral, which is 3-dimension with 2-dimensional domain, right? Okay. Yes, we increase the dimension, but at the same time, if you think about it, the curl of f has partial derivatives. Okay, and that partial derivatives may eliminate some functions down to 0. Okay, as I can show you here, when we compute the curl of vector field f, that dou x, dou y, dou c, the vector field may be quite complicated, negative y squared, x and c squared, but when we apply the curl of that, you see in the first component we get 0. The second component we also get 0. The third component we get 1 plus 2y, which is a lot nicer compared to the vector field itself, right? Now, next, how about the ds? The surface S, actually y plus c equals to 2, right? If we call this function g, then the gradient of g, which is the vector function normal to surface g, will be 0, 1, 1. Okay, notice that we will get the same result if you have solved it this way. You say z equals to 2 minus y, c sub x is 0, c sub y is negative 1. So the factor normal to that will be 0, negative of negative 1, 1. Right? Negative c sub x, negative c sub y, 1. Remember that? Okay, so we will get the same thing. Okay, now then when we put things together, double integral over s curl of f dot ds, that will be double integral over still, yeah, it is over s, right? The curl of f is 0, 0, 1 plus 2y dot 0, 1, 1 dA. Oh, since I already used dA, then it's supposed to become a d down here. this d here. Okay, so we have double integral over d of 1 plus 2y dA. Now we can make it into polar, 0 to 2 pi. I think the radius is 1, is it right? Yeah, the cylinder has radius 1. Of 1 plus 2 r sine theta, I'm sorry, no, r dr sine theta, the r dr d theta. And you will see that the integral over sine theta from 0 to 2 pi, that will give us 0, right? Just for that part. So this is integral from 0 to, let me go back. This is basically double integral of d of r dr d theta, which is basically the area of, I'm sorry, I just call it, that's area of d, which is pi. Okay, notice that I think the step here is, if you realize when you integrate this, right? Okay, you will see integral from 0 to 2 pi of sine theta d theta, that's equals to 0. Okay, so we only deal with double integral of 1 r dr d theta, which is the area of d. Okay, now, so I hope this way you see the purpose of doing this, converting this single line integral into double surface integral is, there's a trade-off there, even though we increase the dimension, but at the same time we deal with the derivative of the vector field. Okay, the curl of f. Okay. Let's see example 2. In example 2, we have this question. Use Stoke's theorem to compute the double integral for a surface that looks like this. That surface is part of the hemisphere with radius 2. Inside the cylinder with radius 1 above xy plane. Okay, now notice that what we are about to compute is the double integral over S curl of f dot ds. We know that is equals to integral over closed curve of the boundary of S f dot dr. Okay, now we can see there that the intersection between x squared plus y squared plus c squared equals to 4 and x squared plus y squared equals to 1, the intersection of that will give us 1 plus c squared equals to 4, c squared equals to 3, z equals to radical 3, right? Because we want above, it's supposed to be plus minus above, right? But c is at least 0. Okay, so we use only the positive branch. Okay, now then the c, the intersection, can be parameterized by rt, where we have a cosine t, sine t. Remember, it is in the cylinder with radius 1, and the c is square root of 3. Right? Okay, so instead of computing the curl of that double integral, we will compute the integral over closed curve C of f dot dr. Okay, now, So what is r prime t? R prime t is negative sine t cosine t 0. Okay, and integral from 0 to 2 pi. What is the f again? The f is the x is cosine t, the z is radical 3, the y is sine t, the z is radical 3, and xy is cosine t sine t. That's the vector field f. Dot r prime t, which is negative sine t cosine t 0 dt. This is the r prime t dt, which is dr. Okay, this is equal to integral from 0 to 2 pi of negative radical 3 sine t cosine t plus radical 3 sine t cosine t plus 0, right, dt. But it gives us integral from 0 to 2 pi of 0 dt, which is 0. Okay, nice thing, right? Okay, let's go on. Note, if the boundary of surface 1 equals to the boundary of surface 2, and all the requirement for Stokes theorem being satisfied, then double integral over surface 1 of curl of vector field f dot oriented s equals to integral over closed curve the boundary of S1, which is also equals to the boundary of S2 of f dot dr, which is equals to double integral over surface 2. Notice that they share the boundary, right? Okay, double integral over surface S2 of curl of vector field f dot ds. Think of it this way. Think of it this way. If I have a surface S1 that shares the same boundary with another surface, let's call that surface S2, they happen to share the boundary, then both of them can be represented by integral over closed curve of the boundary of f dot dr. Okay, actually we can use example 2 again. We can use example 2 here to work on that. Okay, let's take a look. If I redo this example 2, notice that that surface S, which is the cap, I think I should draw it this way. This is the cap, right? That S share the same boundary with this. Is it right? Think about it. Okay, let's call this S2. Okay, let's call that S2. So double integral of S of curl of f dot ds should be equals to double integral over S2 of curl of f dot ds. Is right? Now the nice thing about S2 is the vector normal to it is 0, 0, 1. Okay, now so what is the curl of that vector field F? I, J, K of dou X, dou Y, dou C of X, C, Y, C, X, Y. That will be X minus Y, negative of Y minus X, 0. Okay, now you see this is ugly, this is ugly, this is nice. This is nice, nice, not so nice. But when we do the dot product, let's see what happened. When we do the dot product, right? So double integral over S2 of curl of F dot ds, this is equal to double integral over S2 of X minus Y. Actually, this is also X minus Y, huh? X minus Y 0 dot 0 0 1 dA. Okay, which is double integral over 0. That's 0. Okay, so instead of computing the double integral of curl of vector field F of the original surface S, you can compute using Stokes' theorem the line integral over closed curve of F as the way our textbook does it, or you can apply quote-unquote what I call double Stokes theorem. Okay, so instead of computing the surface integral over that ugly surface, you compute the double integral over a nicer surface. Okay, you purposely choose a surface whose normal factor is a lot easier to use. And in this case, as you can see, however ugly the curl of F, okay, when you do the dot product against 0, 0, 1, it turns out to be a scalar 0. Okay, so that's the basically the Stokes theorem. Now let's do some problem. Okay, to emphasize what I teach you, what I said earlier about that double Stokes theorem, let's take a look on question number 1 in our textbook. I will not do this though, but I just try to explain to you what I meant by double Stokes theorem. Take a look here. This is question number 1. Okay, where H is the hemisphere and P is the portion of paraboloid. Okay, suppose F is a vector field on R3 in space whose components have continuous partial derivatives. Explain why this curl here, double integral of curl over the hemisphere, equals to double integral of the curl over the paraboloids, the boundary of the paraboloids. Well, first because they share a common boundary. Okay, let me make it thicker so that we can see better. They share common boundaries. Okay, this is dou H and this is the boundary of the paraboloids. Happens to be the same. They're equal. Okay, which means this is equals to the integral over closed curve of dou H, which is also dou P of F dot dr. Okay, in fact we can say something more, right? We can say something more. This is equals to double integral over the domain D, which is basically the flat circle on xy plane. of curl of f dot ds, which is dot 0, 0, 1 dA, right? If this is our d. Okay, so this is let me use different color. Let's go, this is the d, okay, which is the bound, the base of this hemisphere, the base of this paraboloid. Okay, that's for question number 1. It's more about conceptual question though, but I hope through this Stokes theorem you see how convenient it is that you now have more options on how to do a double integral or a closed curve integral. Okay, let's do more problem. Suppose we are use Stokes theorem to compute question number 2. Use Stokes theorem to evaluate this double integral. Well, instead of computing that double integral, let's do the closed curve integral. Okay, now so you see you have a hemisphere, so x squared plus y squared plus c squared equals to 9. That's hemisphere with radius 3, right? Okay, now notice that the boundary is actually coincide, is on the ground, right? Okay, so we can use just single Stoke first. So the first method, method 1, let's parameterize that C. If this is the surface S here, let's parameterize that C. Okay, so C is parameterized by RT, radius 3, right? So 3 cosine t, 3 sine t, comma 0. The t is from 0 to 2 pi. Okay, now the vector field F now, if we use RT to parameterize that, will become 2y cosine 0 e to the x, what is my x? 3 cosine t sine 0, and then x e to the y. You see how ugly it is? Are you sure you want to deal with that? Okay, now then, if you want to compute that double integral over surface S of the curl of f dot ds, that is the same to integrate over closed curve of C of f dot dr. Let's see, what is our dr? So r prime t will be negative 3 sine t, 3 cosine t 0. Okay, now notice what happened to the dot product. Let's go, don't do this for now, we save it for later. Let's do the dot product first. So f dot dr will be 6 times negative 3, negative 18 sine squared t, cosine 0 is 1, comma. For the y component, cosine 0 is 0. I mean, sine 0 is 0. Okay. For the z component, this guy times this guy is 0. Right? dt. Okay. So now our closed curve integral from 0 to 2 pi of negative 18 sine squared t dt, that is equals to -9 integral from 0 to 2 pi of 1 minus cosine 2t dt, which we know if I do the integral here for the cosine 2t over that interval 0 to 2 pi, that will give me 0. Okay, so I will end up with -9 times 2 pi, which is -18 pi. Okay, suppose instead I do double Stokes theorem. So method 2, the terminology is double Stokes theorem. It's my terminology. Okay, so I think if you say double Stokes theorem to other students in calculus 3, they may not understand what you meant. But this is my terminology, double Stokes theorem. So you apply that back where you notice that the boundary of a surface S, which is C there, actually the same boundary for this surface. Let's call this D. Let's call that D. Okay, so double integral over surface S of curl of F dot ds is equal to double integral over D of curl of F dot ds. The nice thing about that D is the ds is 0, 0, 1. Okay, what we need to do, however, is to compute the curl of F, right? But knowing we just need the last component of curl of F, so what is my, that's 2y cosine c, 2y cosine c. For the x component, I'm sorry, I need to go back and forth, e to the x sine z, e to the x sine z, and then the last component of vector field F is x e to the y, x e to the y. Now, if you remember, the third component of the curl of F is q sub x minus p sub y, right? Which is q sub x is e to the x sine z minus p sub y, that's 2 cosine z. Is it okay? Okay, but D has z equals to 0, right? Therefore, the curl of F there will be something 0 minus 2 cosine 0, which is 0, 0, -2. Right? Do you think it's really nice? So now our double integral over D of 0, 0, -2 dot 0, 0, 1 dA, that is double integral over D of -2 dA. That's -2 times the area of D. That's -2 times 9 pi. Okay, that's for number 2 from our textbook. Okay, according to our textbook, they want you to do with Stokes theorem. Okay, here I provide you 2 ways. Okay, one is the actual regular Stokes theorem. The second method is, well, if the boundary happens to be represented by as the boundary of a simpler, nicer surface whose normal factor is super nice, then you may want to just do it that way. Okay, you do apply double Stokes theorem. Okay, let's see number 6. Honestly, I randomly pick even numbers though. Okay, but if I were you, I will practice a lot more with odd numbers, and then make sure you check with the back of the book. Okay, number 6. S is half of the ellipsoid that lies to the right of XC plane, oriented in the direction of positive y-axis. So you have this XC plane. We have that ellipsoid, right? 1, and then 2, and then 1. So we have this ellipsoid here. That ellipsoid. I hope this helps us see what actually happened there. Right? Now notice that the boundary of that ellipsoid is this. This is the boundary. Right? Okay. So suppose we need to compute a double integral over surface S of curl of f dot ds. We want to use the boundary of S. Let's call that C is parameterized by RT. The y component is 0. The x component is what? When you set the y equals to 0, when you set the y equals to 0, then you get 4x squared plus 4z squared equals to 4, x squared plus c squared equals to 1. Right? So let's use cosine t for the x component and sine t for the y component, for the z component, where t is from 0 to 2 pi. Okay, so r prime t is negative sine t, 0 cosine t, and the vector field f using the parameterized by that t will be e to the xy, that will be 0, which is 1, e to the xc, e to the sine t cosine t, and then the z component will be x squared c cosine squared t sine t. Okay, now this is integral over closed curve c of f dot dr. Okay, so integral over closed curve c of f dot dr will now becomes integral from 0 to 2 pi of 1 e to the sine t cosine t cosine squared t sine t dot cosine t, I'm sorry, negative sine t, negative sine t 0 cosine squared t sine squared. What am I doing? No, I should not do the dot product yet. It's still just the r prime t. So cosine t dt. Now this becomes integral from 0 to 2 pi of negative sine t plus 0 plus cosine cube, cosine cube t dt, cosine cube t sine t dt. Okay, but you know, when you integrate sine t over integral of over interval 0 to 2 pi, this goes to 0, and you will see this also goes to 0. Okay, just integrate it properly, then you will see that you still end up to 0. Very nice number. Okay, now this is method number 1, in which I instead of using the double integral over the surface S, I use single integral over curve C. Okay, now if you notice, the boundary of this this closed curve C here actually also a boundary of this guy D, which is a flat plane on XC plane. Okay, and a flat plane on XC plane. So suppose I use double Stokes followed by double Stokes theorem. Double integral over surface S of curl of f dot ds is equals to double integral over d of the curl of f dot ds. Okay, now the nice thing about that surface D, the normal factor will be in the positive y direction. Okay, it's 0, 1, 0, right? Okay, so when we do the curl of that f for that D, we just need the second component. The curl of f is ijk dou x dou y dou c of what's that, e to the xy, e to the xc, e to the xy, e to the xc, and then x squared y, right? Now remember, I just need the second component. The second component is negative of 2xy minus 0. Okay, so curl of f dot ds will later on give us negative of 2xy, negative of 2xy dA. Oh, but don't forget that on at D, on surface D, the y equals to 0. Okay, so then our double integral over D of curl of f dot ds is double integral over D of 0 dA. That's just 0 as we expected. It's just like the curl kills something, the surface D kills another thing, and then when you put them together, everybody died. Okay, that's question number 6. Let's go on further. How about question number 8? In question number 8, we basically go backward. Okay. Use Stoke's theorem to evaluate that integral over curve C of f dot dr. And in each case, C is oriented counterclockwise as viewed from above. C, number 8. C is the boundary of part of the plane in the first octant. Oh, okay. So this means the x-intercept is 1/3, 0, 0. The y-intercept is 1/2, 0, 0. 0, 1, half 0. And the c-intercept is 0, 0, 1. That is the surface. Okay. Now, according to our integral, suppose we do it a standard way, like the way we did, I think 16.2 or 16.3. Okay, integral over closed curve C of f dot dr. We're supposed to see that as integral over C1 plus integral over C2 plus integral over C3. Is it right? It's supposed to be like that. So it's supposed to be integral over C1 plus integral over C2 plus integral over C3 of f dot dr. Supposed to be like that, right? But no, we don't want to do that. Why? It seems like we will work very hard. So instead of doing it that way, let's use Stokes' theorem instead. So let me erase this. So it's double integral over surface S of the curl of f dot ds. Now, why do you want to do the curl? Because the curl may kill something. At the same time, we know that surface S, okay, has a normal factor 3 to 1, right? Suppose this is our G, right? Suppose this is our G. Then the gradient of G, which is the normal factor, the factor normal to the surface, will be 3 to 1, right? Okay. Now, like on the other hand, curl of vector field F is I j k of dou x dou y dou z of 1 x plus y z xy minus square root of z, that is x minus y for the x component minus y minus 0 and then 1 minus 0. So the curl of f will be x minus y minus y 1. So what happened with the curl of f dot ds? That will be x minus y negative y 1 dot 3 to 1 dA. That is 3 times x minus y minus 2y plus 1 dA. That is 3x minus 5y plus 1 dA. Hopefully I don't make any miscomputation. Okay, so double integral over S of curl of f dot ds will be equal to double integral over d. Now what is d? This is d. This is d here. We project that down, right? Because you see it's oriented counterclockwise viewed from above, right? So it must be projected to xy plane, okay? Of 3x minus 5y plus 1 dA. Okay, now let's see the ground. On the ground D, we have 1/3 here and then 1/2 here. What is the equation? When C equals to 0, this is 3x 3x plus 2y equals to 1. So the integral from 0 to 1/3, integral from 0 to y will be 1 minus 3x over 2 of 3x minus 5y plus 1 dA. Okay. I don't really want to integrate that one though. Honestly, why? Because double integral over 1 dA is basically the area of the triangle D. Okay, I'm sorry, it should not be dA right now. It should be dy dx. And then we just integrate it then. Okay, we just integrate. I have time, so let me just do it. Integral from 0 to 1/3. Okay, 3x y minus 5/2 y squared plus y from 0 to 1 minus 3x over 2 dx. So this will be 3x times 1 minus 3x over 2 minus 5/2 1 minus 3x over 2 squared plus 1 minus 3x over 2. Let me use this one instead. Give me a second. Now we need to simplify the painful part. 0 to 1/3. That will be 3/2 x minus 9x squared over 2 minus 5 over 8 plus what is that? 3 times 15 over 2x. And then I'm sorry, that's a square. What am I doing? 15 over 4. And then minus 9 times 5, 45 x squared over 8 plus 1/2 minus 3x over 2. Oh, something cancel. Oh, I didn't realize that. This guy cancels with this. Anything else cancels? At least that part. Okay. Integral from 0 to 1/3 of, let's start with the x squared. So that will be negative 54 over, no, not 50, sorry, negative 9 over 2 is multiplied by 4, negative 36 over 2x squared plus 45 will be negative 81 over 2x squared plus 15 over 4x minus negative 5 over 8 plus 4 over 8, that's negative 1/8 dx. And then from there we integrate. Negative divided by 3, that will be 27 over 2x cubed divided by 2 plus 15 over 8x squared minus 1/8 x from 0 to 1/3. That's negative 1/2 plus 15, 5 over 3, so 5 over 3, 5 over 24 minus 1 over 24. So negative 1/2 plus 4 over 24. That is, the LCD is what? 3 over 6 plus 1 over 6. That's negative 2 over 6, which is negative 1/3. I hope I don't make any miscomputation though. Okay, I know my setup is correct. Okay, anything after that, just computation, which again, I hope I don't make any mistakes. Okay, now, of course, I think another question is, Thomas, is there any way for us to apply double Stokes theorem? I don't think so. The thing is, like, this plane that we have here, this surface that we have here, is actually a very nice surface. Okay, and any surface that has the same boundary must be uglier than this surface. Okay, that's why seems like we have to work with that surface, right? Okay, and then yeah, we project that down to the ground. Therefore, we get this double integral. Okay, that's for number, what number is that? Number 8. How about number 10? We have that F, vector field F, and C is the curve intersection of the plane x plus y equals to 5. So let's say x plus y equals to 5. Intersect with a cylinder with radius 3. So the intersection will be something looks like this, right? That's the curve C. Okay, let's see how to parameterize that. So C is managed by RT on XY plane. On XY, that's a circle with radius 3. So 3 cosine T, 3 sine T, x plus y equals, I'm sorry, x plus C equals to 5. That's the surface, by the way. So the C will be 5 minus Z. Okay, so R prime T equals to negative 3 sine T, 3 cosine T, 3 sine T. The vector field F on that curve will be xy, 9 sine T cosine T, 2z, so 10 minus 6 cosine T, and 3y, 9 sine T. So F dot dr will be negative 27, no factor notation, negative 27 sine squared cosine T, 30 plus 30 cosine T minus 18 cosine squared T, and then plus 27 sine squared T dt. Once we plug that into once we plug that into integral over closed curve C f dot dr, it's integral from 0 to 2 pi of these things here. sine squared t plus 30 cosine t minus 18 cosine squared t plus 27 sine squared t dt. We know this will be 0. We try to compute it. This will also be 0. Okay. In fact, with some extra knowledge, I think you can see that this, you know what? I want to say that you think about this. I want to say that this is actually 9 times sine squared t dt. Now, you may wonder why. Okay, I argue this way. Integral over cosine squared t dt from 0 to 2 pi is equal to integral from 0 to 2 pi of sine squared dt, sine squared t dt. Okay, try to compute them. You will get the same result. In other words, then, this guy here and this guy here in some sense cancel out and give us only 9 sine squared t. Now, then, this is 9 over 2 integral from 0 to 2 pi of 1 minus cosine 2t. Whose integral, the cosine 3 over 2 pi also 0. Okay, so this will give us 9 over 2 times 2 pi, which is 9 pi. Okay. That's if we do it regularly, right? Suppose we use Stokes' theorem. See, this one here, I computed using regular way. I didn't use Stokes' theorem. If we do it regular way, we get 9 pi. Suppose we use Stokes' theorem. By Stokes, if we use Stokes' theorem as directed by the book, we use Stokes' theorem. Then the curl of f is I jk dou x dou y dou c of, what is my f, xy 2c 3y, xy 2c 3y. Am I copying it correctly? xy 2c 3y, whose curl will be 3 minus 2 0 x. That's 1 0 x. That's the curl of f. Now how about surface S? Surface S has normal factor. Surface S is perpendicular to 101. Okay, so that integral over closed curve C of f dot dr is, according to Stokes' theorem, is double integral over S of curl of f dot ds, which is double integral over surface S. The curl of f is 10 x dot 101 dA. But if I do 101 dA, then it will be a d already, which is this with radius 3, right? That's a this with radius 3. Let's write it nicer first. That will be 1 plus x dA. That's integral from 0 to pi, integral from 0 to 3. Is it right? 3 or 4 or 1? Yeah, that's right. okay, of 1 plus r cosine theta r d theta. Okay, but then you can see that if you integrate this will give us 0, and this is basically double integral over 2 pi. Maybe I write it this way. It's double integral over d of 1 dA. That's area of d, which is 9 pi. Okay, that's question number 10. Let's move on to question number 14. I will do 2 more problems and then give you suggested homework. After that, we take a break. Number 14. You see, we basically practice. Number 14. Verify the Stokes theorem is true. So we basically need to show 2 different ways to do that. So we basically need to show that double integral over surface S of the curl of f dot ds, if we compute it this way, we're supposed to get integral over closed curve of the boundary of S of f dot dr. Okay, that's what we want. Now let's see. S is part of the paraboloid that lies above this plane z equals to 1 oriented upward. So we have a paraboloid 5 minus x squared minus y squared. This is the paraboloid. Okay, above the z equals to 1. Okay, now let's compute the left hand side first. The left hand side. So the curl of vector field F is ijk dou x dou y dou z of negative 2yc, y, and 3x. That gives us 0, negative 3, negative of 3 minus negative 2y plus 2y, and then 0 minus plus 2c. That's the curl of f. Okay, now that surface S is normal to the vector 2x 2y 1. Okay, so when we compute the curl of f dot d oriented S, that will be 0 for the first component. That's 0 times 2x plus 2y times negative, write it this way, minus 3 plus 2y times 2y, and then plus 2z. Okay, that is equal to 0. So negative 6y minus 4y squared plus 2z. But our z on that surface is 5 minus x squared minus y squared, right, on that surface S. This will be 10 minus 2x squared minus 6y squared minus 6y. Oh, this is quite nasty, huh? Now I need double integral over s of curl of f dot ds. Oh, I'm sorry, this is supposed to be with dA. It's differential form, right? That is equals to integral over I'm so lazy to do it honestly. What is this though? When c equals to 1, so that will be x squared plus y squared equals to 4, less than equals to 4 supposed to be. So that will be double integral over that d of 10 minus 2x squared minus 6y squared minus 6y dA. Because the domain is symmetry with respect to x and y. Yeah, the domain looks like this. The domain looks like this with radius 2, right? Okay, so I can just make it like this. So let me polarize that 0 to 2 pi, 0 to 2, 10 minus 2x squared minus 6y squared minus 6y. Oh, what am I doing? I need to make it into polar already. I want to argue that double integral over x squared dA is equals to double integral over y squared dA on that domain D. Okay, because the domain is symmetry. Okay, so I can just say this is negative 8 y squared, which is r squared sine squared minus 6r sine theta r dr d theta. Okay, now this gives us the first part. Let me mark it this way. This guy here will give us 10 times area of D. Okay, now this will go to 0. Okay, while this guy here will give us minus 8 times integral from 0 to 2 pi of sine square theta d theta times integral from 0 to 2 of r cubed dr. What is area of D? 4 pi. So this is 40 pi minus 8 times pi. This will give us pi. You try to check that. And this will give us 4. I think so. 4. 16, yeah, that will give us 4. So 40 pi minus 32 pi, that's 8 pi. Okay, that's what we get if we just use double integral over curl. Okay, let's see what happens if I do the integral over closed curve C f dot dr. Okay, so the C is parameterized by 2 cosine t, 2 sine t, the z is 1. So r prime t will be negative 2 sine t, 2 cosine t, 0. This is for t from 0 to 2 pi. Okay, and f, the vector field on that RT will be When I parameterize that, there will be negative 2. The y is 2 sine t. The c is 1. That's for the x component. For the y component, 2 sine t. The c component, 3 times x, so 6 cosine t. So the dot product f dot dr will be f dot dr f dot dr. So that would be 8 sine squared t plus 4 sine t cosine t plus 0, right? And the integral over closed curve cf dot dr will be integral from 0 to 2 pi of 8 sine squared t plus 4 sine squared t sine t dt, sine t cosine t dt. You know what? This may take too much space. Let me do it this way. Underneath. I will do the underneath. Let me do it here. What do I have earlier? 8 pi. Now you will compute, you will see that, you will see this guy goes to 0. Okay, well, this is actually 8 times pi. Okay, I think using Stokes theorem is easier, right? I think using Stokes theorem is easier. In fact, I think using double Stokes theorem is even easier. By double Stokes. You apply you apply Stokes theorem twice. Notice that the D is the surface C equals to 1, okay, which is normal to 0, 0, 1. Okay, now the curl of F, we computed earlier up here. The curl of F is this, right? This is the curl of F. Let me lock that. The curl of F is this, right? But for C equals to 1, we get 0, negative 3 minus 2y, 2. Ah, don't you think it's so nice? Right? Because what? The curl of F dot ds, that's basically blah, 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 2 for the curl of F dot 0, 0, 1, which is 2. Okay, so double integral over d of curl of F dot ds is equals to 2 times area of D. But our D is the circle with radius 2. That's how I get 2 times 4 pi, that's 8 pi. I hope at this point you see how useful it is to use double Stokes. If the boundary happens to be on a flat plane. Okay, so you see, for this one question here, number 14, we just need to verify Stokes theorem is true, right? In fact, I show that Stokes theorem is true even if you apply that twice. Okay, let's do the last one. I was planning to do number 16. This is a nice one, actually. Let C be a simple, closed, smooth curve that lies on the plane x plus y plus z equals to 1. So the surface S is given by x plus y plus z equals to 1, which means it is the factor normal to it is 1, 1, 1. Okay, now show that the integral over closed curve C for any closed curve for on the region enclosed by C, not on the shape of C or on the location of C. So for any C, on X on that surface S. Okay, so integral over closed curve C of f dot dr is equals to double integral over S curl of f dot ds, right? Let's take a look. What is our f? Our vector field f is, take a look, the x component is z, the y component is negative 2x, the c component is 3y, right? Can you see that? We can rewrite this as integral over curve c of c negative 2x 3y dot dr, right? Okay, so what is our curl of vector field f? Three, 1, negative 2. I hope I get it right. Okay, so when I do the dot, so curl of f dot ds, that is equal to 3, 1, negative 2 dot 1, 1, 1 dA. That's basically 2 dA, right? Okay, so double in the integral over s of 2 dA will be, oh, hold on, my dA, once I change it to dA, you call this the ds here. ds. No, it should be dA already. Should be dA already. But since I use a here, then this should be d. What I meant is the surface is this guy. This is our surface S. Is that right? Now our D is the one on the ground. Okay. Now the thing is, it is as long as it is on the surface S though. Now imagine if you have, let me enlarge this. Actually, it's incorrect for me to say this is the D. Suppose I have the curve on S that looks like this. That's the curve on S, right? The projection of that will be this. Okay, so this is my D here. Okay, so basically that's equals to 2 times the area of that D. Okay, the area of the projection of that surface, maybe let's say this is C, this is C, this is C here. Okay, so the projection of that C give us the boundary on the ground, right? And that boundary on the ground encloses D, and we need to compute the area of the D multiplied by 2. That's our result. Okay, notice that we can find the result of this integral without even knowing what is C. What C is, yeah, without knowing what C is. Okay, notice that the area enclosed by C. Okay. Suggested homework from here. Suggested homework will be from this section 16.8 will be number 1 to number 11 and then 13 to 19. Okay, I will stop here.